All right, hello again. In the previous lesson, we solved nonlinear systems and applications. Now we're going to move to a new idea called counting principles, permutations, and combinations. You can take a minute to look at the quick rules for this lesson. We're going to review them as we go throughout this lecture today. All right, so example number one, we're going to use the counting principle. So a student has 4 shirts, 3 pairs of pants, and 2 pairs of shoes. How many different outfits are possible? Okay. Now, when we're looking at this problem, we need to understand something. For every shirt, there are 3 pairs of pants. Okay. We have 4 shirt choices, and for every pair of shorts or shirts, we have 3 choices for the pants. So we have 4 choices. We have 3 pants choices, and then we have 2 sets of shoes. Okay. So what we can do is use the fundamental counting principle. The fundamental counting principles multiply the number of choices at each stage. So this is essentially saying 4 times 3 times 2. So 4 times 3 would be 12. And then 12 times 2 would be 24, or 24 possible outfits. Okay. So again, that's multiplying at each stage. 4 times 3 times 2, that's 12. And then 12 times 2 gave us 24. Okay. Just very, very important. Okay. And so we multiply because one choice is being made from each category, right? One choice is being made from each respective category. All right, let's continue. Now, this is using um, ordered arrangements. How many ways can 5 different books be arranged on a shelf? Okay, so think about it. If you put one book up there, then if you got 5 books, you can arrange them in any particular way, right? Write the answer using factorial notation. So first of all, in the first position, we have 5 choices. Then after choosing the first book, we have 4 choices that remain. Then we have 3 choices that remain after that, and then so on and so forth, right? Because we have 5 choices the first time, we only have 5 books. Then after we put that first book up there, then we'll have 4 books to choose from. So 4 choices, 3 choices, so on and so forth. So what that means is essentially 5 times 4 times 3 times 2 times 1. So this can be written as 5 factorial. Okay. So this can be written as 5 factorial. All right. 5 factorial is the same as saying 5 times 3 times 4 times 3. Oops. 5 times, got a little ahead of myself. 5 times 4 times 3 times 2 times 1. And in this case, is going to be equal to 120. So 5 factorial is equal to 120. And again, that's 5 times 4, which is 20. 20 times 3, which is 60. 60 times 2 is 120. Times 1 would be 120. So essentially, we have 5 choices in the first category. Then we have 4 choices, 3. So there's 120 different ways to arrange 5 books. That's essentially what this argument is saying. Mathematical argument. All right, pause and try this problem. So it says a class has 12 students. How many different 4 student committees can be formed? State why order does or does not matter. All right, pause and try this problem. All right, so in this problem, there's no such thing as, first, second, third, fourth, or fifth in this arrangement, right? So, order doesn't matter. 12 students being arranged in 4 student committees, a committee is simply a group. So order doesn't matter. So when order doesn't matter, we use the combination formula. So the combination formula is N C or N combination R, which equals N factorial divided by R factorial parentheses N minus R factorial. So in this case, we have N. N is the number that we're looking for, counting 4. We're going to set that equal to N, which is 12 factorial, divided by R, which is going to be 4 factorial. And then we have N minus R, or 12 minus 4 factorial. Simplifying this, we have 12 factorial, and we have 4 factorial, and then this will be 8 factorial. Now, what we can do here is we can expand. I'm going to expand both of these to show you. So we have essentially 12 times 11 times 10 times 9. And then I'm going to leave that as 8 factorial, right? Because 8 factorial is simply 8 times 7 times 6 times, etc. But I want to simplify this problem. Okay. So what I can do here is I can simplify these 8s, right? So this would be 12 times 11 times 10 times 9 divided by 4 times 3 times 2 times 1. Now, the denominator gives me 24. 4 times 3 is 12. 12 times 2 is 24. And then let's see, 11 times 12 times 10 times 9. That is going to give me 11,880. So when I simplify this, I get 12 counting 4 equaling 495. Okay, and again, for a class of 12 students, how many different 4 student committees we can make? We can make 495. Okay. All right. 495 committees is possible. All right, let's continue. All right, so here we have example number 3. This is a permutation problem. So from 10 finalists, how many ways can first, second, and third place, right? So first, second, and third place be awarded. So you have 10 finalists. So winning first place is different from winning second or third, right? So this is why we're going to use permutation. So the permutation formula is NPR equals N factorial divided by N minus R factorial. Okay. So we're looking for 10. So we have 10 permutation R, which is going to be 3 in this case. Substituting the values in here, we have 10 factorial. N is going to be 10 minus 3 factorial. Okay. Simplifying it, we have 10 factorial and 7 factorial. We can do 10 times 9 times 8 times 7 factorial. 7 factorials cancel. We're left with 10 times 9 times 8. 10 times 9 times 8 is going to give us 720. So out of 10 finalists, the permutation of first, second, and third, because those are the only possible, we would get 720 possible award results. Okay. Let's continue. This is a password application problem. So a code uses two different letters followed by three different digits, right? So two letters, and then this is assuming that we're using the ABCs, and then we have three different digits. So there's 10 possible digits here, respectively. Repetition is not allowed. How many codes are possible? Okay, so the way this is going to look is we have letter, letter, digit, digit, digit. Okay, and again, there are 26 choices for the first letter, and then it'll be 25 choices for the second letter. So 26 times 25. And then for the first digit, there are 10 choices. Zero may be used because this is a code, not a three-digit number. So the first is 10. After using one digit, 9 remain. That would be 9. After using two digits, 8 remain. 8. So what we need to do is use the fundamental counting principle. So 26 times 25 times 10 times 9 times 8. Okay, so first of all, 26 times 25 is 650. And then 10 times 9 times 8 is 720. So 650 times 720 is 468,000. Okay, so there are 468,000 codes. Okay, which is pretty amazing. So the number of available choices decreases because repetition is not allowed. All right. If repetition was allowed, then we'd obviously have more codes. Okay. All right. So common mistake, decide whether order matters. A student uses permutations to select 3 pizza toppings from 8 choices. Explain whether a permutation or combination is appropriate and why. Okay. So the student used the wrong method. When selecting pizza toppings, the order in which the toppings are named does not change the pizza, right? So for example, if you do beef, chicken, and olives, right? Beef, we'll do beef, chicken, and onions. Okay, we'll keep it low calorie. All right. Is the same toppings selected as, say, chicken, beef, onions? So again, notice if I selected this on the first pizza and then this on the second pizza, does it really matter? The order changed, but the group of toppings did not. Okay. So therefore, order does not matter. Okay. So that's first of all. So he used permutations to select that, which was, essentially incorrect. So what he should have done was used combination. So in this case, let's help him correct the choice. So 8 combination 3 is the same as 8 factorial divided by r, which is going to be 3 factorial. And then n minus r, that would be 8 minus 3, which would be 5 factorial. Then we can simplify. We can do 8 times 7 times 6 divided by, matter of fact, we'll do that 5 factorial. So the 5 factorials will cancel. Then we'll have 3 factorial, which would be 8 times 7 times 6, all over 3 times 2 times 1. So 8 combination 3 would be, what is this? 336 divided by 6. So that would be 56. Okay, that would be the final answer. So there's 56 topping combinations. according to his scenario. 3 pizza toppings, 8 choices. Well, then you have 56 topping combination. Okay. Use a permutation only when changing the order creates a different outcome. Using a combination only when the selected group matters. All right. So let's review. So again, the fundamental counting principle, you will multiply essentially across stages. All right, which is what we did here. So if you're trying to find something to wear, you got 4 shirts, 3 pants, 2 shoes, then you can multiply them together, and then that'll tell you, okay, I got 24 possible outfits. When you're counting, so in an arrangement like this, notice the reduction of options exists because you have 5 choices the first time. Once you lay that book down, then you only have 4 choices, so that's 5 permutation. When you're choosing a committee, order doesn't matter, so you need to use the combination formula. And when order actually matters, or essentially when you only have the option of having a first place, second place, and third place and nothing else, then you need to use permutation. In the event of you're given a password and when it says that repetition is not allowed, then notice you have to reduce the number of options as you go on. So that'd be 26 letters possible, 25 letters possible. And then we include 0 in this. So we're saying that 10, 9, 8. And then if we had to continue going on, then we would, the result would continue to decrease. Okay. So again, this has been video 18, part 1, counting principles, permutations, and combinations. And thank you again for watching. I hope to see you in the next one.